Hi friends, hope last classes were useful to you. In this class, we will solve examples of series parallel connected resistive networks and also study about star delta combination of resistances. In this example, it is asked to calculate the effective resistance between points A and B for the combination of resistances given in figure. That is, we have to calculate the resistance between A and B for this combination of resistances. First 15 ohm resistance is coming, then 3 resistances are connected like this. See, in this point, you can see that this 20 ohm, this 10 ohm and this 20 ohm is coming to a common point, and here also the other point of the 20 ohm, 10 ohm and 20 ohm is coming to a common point. That is, this 20 ohm, 10 ohm and 20 ohms are coming in parallel. In parallel combination of resistances, effective resistance here Rp is equal to 1 by Rp is equal to 1 by first resistance 20 plus 1 by 10 plus 1 by 20. Here LCM is coming as 20. Dividing this LCM by this 20 and multiplying here, it will come as 1. Similarly, 20 by 10 into 1 is equal to 2 plus next term comes as 1. That is equal to 4 by 20. That is 1 by Rp is equal to 4 by 20. Inverting both sides, Rp is equal to 20 by 4, that is equal to 5 ohm. So our diagram can be simplified as this 15 ohm coming in series with this 5 ohm and going to point B. As 15 and 5 are in series, it can be added. So total resistance becomes 15 plus 5, that is equal to 20 ohm. In this problem, we are asked to calculate the effective resistance between A and B, in which resistances are connected in parallel, which is coming in series with this 18 ohm, and this combination is coming in parallel this one, and then this much combinations are going in series to this 5 ohm resistance. First we will take 3 ohm and 6 ohm which are connected in parallel. So resistance between point C and D is 1 by RCD is equal to 1 by 3 plus 1 by 6, that is equal to 2 plus 1 by 6, that is 3 by 6 or 1 by 2. Therefore RCD is equal to 2. So the diagram can be drawn as 2 ohm, then comes this 18 ohm, and parallel to it comes the 20 ohm, and then in series 5 ohm. As these 2 ohm and 18 ohm are in series, effective resistance is 20 ohm, 2 plus 18. Here between C and E, 20 and 20 are coming in parallel. So 1 by RCE is equal to 1 by 20 plus 1 by 20, that is equal to 2 by 20. Therefore RCE, resistance between C and E, is 20 by 2 or 10 ohm. This 10 ohm is coming in series with 5 ohm. So total resistance between A and B becomes 10 plus 5, that is equal to 15 ohm. In the last class also, we have studied about this type of combinations of resistances. See here, R1 and R2 are coming one after the other, and we studied that this type of connections are called series connections. While here, R5 and R6 are coming as parallel lines, and we studied that it is parallel connection. See now, see in this junction and this junction, here R2, R3 and R4 are coming to a common point. Similarly, here R7, R8 and R9 are also coming to a common point. This is another type of connection. See here, R3, R4 and R5 are connected in such a way that it seems to be like a triangle. So in this class, we will study about this type of connections which are coming to a common point, and also in this connection where 3 resistances are forming a triangle. In this connection, the 3 resistances coming to this junction seems to be like a star, or if it is drawn like this, it is in the shape of a Y. So this type of connections of resistances coming to a junction is called a star or Y connection of resistors. For a connection to be star or Y, it need not be exactly like in this shape. It can be in this shape or in this shape. Only condition is the 3 resistances must come and meet to a common point. See in this diagram, 3 resistances are connected like a triangle. The shape of this seems to be like the Greek letter delta. So This type of connection is generally known as delta connection of resistances. In this diagram, see in this point R1 and R2 are meeting. That is, it is a common point or junction. Such type of junctions where more than one components are meeting are called node. Figure A shows a star connection in which R1, R2 and R3 are coming to node N, while figure B is delta connection in which R12, R13, R23 are there. R12 and R13 are coming to node 1. R12, R23 are coming to node 2, and R13 and R23 are coming to node 3. If these two networks are to be equivalent, then the resistance between any pair of node of the delta connected network must be the same as that between the same pair of nodes in the star connection. First we will see star resistance in terms of delta resistances. Equating resistances between node pair 1 and 2 in figures A and B, R1 plus R2, which is between 1 and 2, is equal to, here between 1 and 2, R12 is connected in parallel with R13 and R3, which are in series. That is, R12 is in parallel with R13 and R23, which are in series. We know that when two resistances are connected in parallel, effective resistance Rp is equal to R1 into R2. That is product of the resistances divided by R1 plus R2. Similarly, here this comes R12 into R13 plus R23 divided by R12 plus R13 plus R23. That is equal to R12 R13 plus R12 R23 divided by R12 plus R13 plus R23. That is, R1 plus R2 is equal to R12 R13 plus R12 R23 divided by R12 plus R13 plus R23. Similarly, for node pair 2 and 3, R2 plus R3 is equal to R12 R23 plus R13 R23 divided by R12 plus R13 plus R23. In the same way, between nodes 1 and 3, R1 plus R3 is equal to R12 R13 plus R13 R23 divided by R12 plus R13 plus R2. This is equation 1, equation 2, this is equation 3. For node 1 and 2, in star connection, R1 and R2 are added, which is equivalent to R12 R13 plus R12 R23 divided by the sum of total resistances in delta. Similarly, between node 2 and 3, here R2 plus R3 is equal to R12 R23 plus R13 R23 divided by sum of these three resistances, R12 plus R13 plus R23. Similarly, between nodes 1 and 3, in star connection, R1 plus R3 is equal to R12 R13 plus R13 R23 divided by the sum of three resistors, R12 plus R13 plus R23. Now subtract equation number 2 from equation number 3. Equation 3 minus equation 2 comes as R1 plus R3 minus R2 plus R3, which gives on the right hand side the denominator is common. So LCM comes as R12 plus R13 plus R23, and here R12 R13 plus R13 R23 minus R12 R23 plus R13 R23. Removing the brackets, R1 plus R3 minus R2 minus R3 equal to R12 R13 plus R13 R23 minus R12 R23 minus R13 R23. Left hand side we can cancel plus R3 and minus R3, and in right hand side we can cancel plus R13 R23 and minus R13 R23. Now the equation becomes R1 minus R2 is equal to R12 R13 minus R12 R23 divided by R12 plus R13 plus R23. Let this be equation 4. The first equation was R1 plus R2 is equal to R12 R13 plus R12 R23 divided by R12 plus R13 plus R23. So now we got R1 minus R2 is equal to R12 R13 minus R12 R23 divided by R12 plus R13 plus R23. Adding equations 1 and 4 gives R1 plus R2 plus R1 minus R2 is equal to, in these two equations, denominators are R12 plus R13 plus R23. So the LCM comes R12 plus R13 plus R23. And here it comes R12 R13 plus R12 R23 plus R12 R13 minus R12 R2, removing brackets, R1 plus R2 plus R1 minus R2 is equal to R12 R13 plus R12 R23 plus R12 R13 minus R12 R23. The whole thing divided by R12 plus R13 plus R23. We can cancel plus R2 and minus R2. Similarly, we can cancel plus R12 R23 and minus R12 R23. Then this equation becomes R1 plus R1, 2R1, and here R12 R13 plus R12 R13, that is 2 R12 R13. Divided by R12 plus R13 plus R23. Dividing both sides by 2, R1 is equal to R12 R13 divided by R12 plus R13 plus R23. R1 is equal to R12 R13 divided by R12 plus R13 plus R23. Let it be the fifth equation. So, if delta connection is to be transformed to a star connection, R1 becomes R1 is equal to R12 R13 divided by sum of the three resistances in that delta connection. In the same way, we can see that R2 is equal to R12 R23 divided by sum of three resistances R12 plus R13 plus R23, and R3 is equal to R13 R23 divided by sum of three resistances R12 plus R13 plus R23. So we studied how to convert a delta connected network into a star connection. For this, three formulas were derived. We need not by heart these formulas. You take any node and the value of R1 which is coming to node 1 is the product of two resistances coming to the same node, that is R12 into R13 divided by sum of three resistances, that is R12 plus R13 plus R23. Similarly, taking the case of node 2, value of resistance R2 which is coming to node 2 is product of R12 and R23 which are coming to the same node divided by sum of R12, R13 and R23, that is R2 is equal to R12, R23 divided by R12 plus R13 plus R23. And while going to node 3, the value of resistance R3 which is coming to node 3 is product of R13 and R23 which is coming to same node 3 divided by sum of three resistances R12, R13 and R23, that is R3 is equal to R13 R23 divided by sum of the three resistances. In this way, we can find the values R1, R2 and R3 of this star connected network from the delta connected network. So, in this class, we have studied how to convert a delta connected resistive network into a star connected resistive network. In the next class, we will study how to convert a star connected resistive network to a delta connected resting network, and how to solve examples using star delta or delta star transformation. I think this class also might have been useful to you. If so, please like it, share it, and subscribe it by pressing that bell button so that you will get all the notifications. Thanks for watching. See you next time.